In today's video, we are going to be discussing alkynes. Alkynes are unsaturated hydrocarbons, just like alkenes. They form a homologous series with the general molecular formula CnH2n-2. The first member of this group of compounds starts with n equals 2. And it has the formula C2H2 and the name ethyne. In terms of hybridization, this group of compounds have the carbon that exhibits sp hybridized orbital. Now the sp hybridized orbital is made of two subshells, okay, and so that's one s and one p, and the remaining p subshells are left unhybridized, so we have 2py and 2pz. Now the functional group for this group of compounds is a carbon-carbon triple bond. Now of these three bonds, we have one sigma bond and two pi bonds. The pi bonds are formed by an overlapping of the unhybridized orbitals. Now for ethyne, with this structural formula, this particular carbon is able to form a sigma bond with hydrogen using the hybridized electrons. So it forms a sigma bond with hydrogen, and it's also able to form one sigma bond with carbon using the hybridized electron. Now for these two unhybridized electrons is able to form a pi bond, which is formed by an overlapping of the unhybridized orbitals from the two carbon atoms. So this is the hybridization that takes place in alkynes, and of course by virtue of being unsaturated, it means that they are able to undergo addition reaction. So we are done with water alkynes. Let's take a look at isomerism in alkynes. For this video, we are going to be considering two types of isomerism for alkynes. That is structural isomerism as well as positional isomerism. Now structural isomerism has to do with whether we have an unbranched chain or a branch chain. So given two structural isomers, we may have isomers that have more branch chain than another, or isomers that simply have a continuous chain. Now for alkynes, let's take an example with n equals 5, which has the formula C5H8. Okay, now if we have a continuous unbranched chain such as this one, with the triple bond at the end, now we have 5 carbon atoms in a continuous unbranched chain. Now in a case where we have a branching out such as this, so we would have 4 carbon atoms in the continuous chain and we would have a branch out. Now this is a structural isomer because unlike in the first case where we have a continuous 5 carbon chain, here we have a 4 carbon chain which is continuous and a branch with 1 carbon atom. So this is structural isomerism. Both of these molecules have the formula C5H8, but in terms of how the atoms are arranged in space, they vary. Okay, now let's take a look at positional isomerism. Now for positional isomerism, it has to do with the position of the functional group in the carbon chain. Okay, so let's take our example with still C5H8. Now for C5H8, we could decide to have a triple bond at the end or at the beginning, and we would have something like this. Okay, 5, and of course carbon is tetravalent, so it would form 4 bonds. Now this has 4 bonds already, so 1 here. Now this has the triple bond at the beginning of the chain. We could decide to bring the triple bond over here. Okay, so we would have something that looks like this. 4 and 5. Now the triple bond here starts with the second carbon atom, and in this case it starts with the first carbon atom. These two molecules are positional isomers because the position of the triple bond has changed. Now bringing the triple bond over here would make no difference, because starting our counting from this position, it will still start with the second carbon atom. So bringing the position here is the same as what we have here. So we have 2 positional isomers for C5H8. This is positional isomerism. It basically has to do with shifting the position of the functional group, or as the case may be, the substituent. Now for this video, we are going to be looking at the two chemical reactions that alkynes undergo, and we'll be looking at addition and combustion. Now when alkynes undergo addition reaction, especially halogenation, they have an intermediate product. So it goes from an alkyne to a substituted alkene, and then to a substituted alkene, So let's take a look at this form of reaction using ethyne, which is C2H2. Okay, so C2H2. Let's draw out the structure for this. The structure for this looks something like this. Okay, now plus let's use bromine as an example. Now of course we know that for bromine, the single bond between the bromine atoms that form the bromine molecule is made of 1 electron from one of the bromines and another 1 electron from the other bromine to form this bond. Now one of the pi bonds between these carbon atoms is also made of 1 electron from the first carbon and another electron from the second carbon. Now we can imagine this, that each of the carbon retracts their electron and each of the bromine retracts its electron. Okay, so this electron would bind with this electron to form a single bond, and then this electron would bind with the other electron here to also form a single bond. So our product, now one of the pi bonds here is broken, but we're still left with 2 bonds, which is 1 sigma bond and 1 pi bond. So we have formed a substituted alkene. Okay, now it's going to look like this with a double bond, and then we would have hydrogen, bromine here, and then bromine here. Now this is the product for this step of the reaction. However, this product is going to be the reactant for the second step. So let's draw it out. Okay, now plus bromine. This is going to undergo this same mechanism of sharing and breaking of bonds, or making and breaking of bonds, and this is going to form a substituted alkane, and this substituted alkane is going to look like this. Bromine here, bromine here. Now the other pi bond is broken and we're left with a sigma bond. Then we have bromine, bromine, and hydrogen. Now this is a substituted alkane. We have that first we started with C2H2 and it reacted with a molecule of bromine to give us C2H2Br2. Okay, this was our product. Now this product went on, it reacted with bromine plus Br2, and then it formed C2H2Br4. Okay, now we can see that the product that we have here is the reactant here. So if we are to sum up these two reactions, this reactant would cancel out the product that we have here, and so in summary, ethyne reacts with two molecules of bromine to give us a substituted alkane with the formula C2H2Br4. Okay, now let's take a look at combustion. In our first video, we came up with a formula, a general equation that would give us a balanced equation for any combustion of hydrocarbon. Okay, now alkynes, just like alkane and alkenes, undergo combustion reaction to give carbon dioxide and water vapor in abundant oxygen, and carbon monoxide and water vapor in insufficient oxygen. Now our equation is CXHY plus X plus Y over 4 O2, which would give us XCO2 plus Y over 2 H2O. Okay, now let's take our example to be ethyne with the formula C2H2. Okay, so we're going to have C2H2 plus 2 over 4, okay, O2, and this would give us 2CO2 plus 2 over 2 H2O. Okay, now we can write this out as C2H2 plus 1 over 2 O2 would give 2CO2 plus H2O. Okay, now we don't want to have a mixed fraction in our equation. We want to have whole numbers, so we can multiply through by 2. Since 1 over 2 is the same thing as 5 over 2, we can multiply through by 2 to get 2C2H2 plus 5O2. This would give us 4CO2 plus 2H2O. Now, checking to see if we have a balanced equation. On the reactant side, we have 4 carbon atoms, and on the product side, we have 4 carbon atoms. On the reactant side, we have 4 hydrogen atoms, and on the product side, we have 4 hydrogen atoms. On the reactant side, we have 10 oxygen atoms, and on the product side, we also have 10 oxygen atoms. So indeed, we have a balanced equation for the combustion reaction. this is the end of our video on alkynes. I hope you enjoyed this video. If you liked this video, please give it a thumbs up and don't forget to subscribe. Thank you.